Okay. Suppose you have got an analog function x a t. X a t has got an analog Fourier transform x capital X a j capital omega. Capital omega is the real life frequency, radian per second. Okay. That is 2 pi into hertz. So, this is related to hertz, megahertz and all those things. So, real life frequency. And suppose I sample it in a sample, a sampling period is t. So, t, 2 t, 3 t like that in a sample here. So, I get a sequence x n this is the nth, this is the first, where x n is the nth sample is this much, that is analog function at this much point of time. And we have seen x n has got discrete time Fourier transform this, fine. But what is the relation between this and this? Because DTFT we have created, we produced an eigen sequence in time domain, calculated the system output, that was eigen function, eigen, that was this DTFT times the original eigen sequence, and thereby the DTFT was discussed and inverse DTFT and all those things, right. But these have been created by us for a sequence. We directly started with an e to the power j omega n, small omega was radian, okay, we called it digital frequency. But what is the relation of this? I mean DTFT with the actual analog Fourier transform of the parent analog signal. The analog signal which was sampled to generate x n, if that has an Fourier transform in terms of the real life frequency capital omega, the DTFT how it is related to that. That is, if I know the DTFT, can I talk about this analog Fourier transform? Can I get it from there? This is the question which is related to sampling and sampling theorem. And this will be covering over this few modules down. For that, we have to go back to the analog signals and observe certain things. One is the Dirac delta function, which is also called impulse, unit impulse function delta t. It is different from the unit sample function we consider in the discrete case. Delta t is defined as this, it is 1, it is 0 if t not equal to 0, and if you integrate area under it is 1. So, delta t actually is a continuous function, it is a function of continuous variable, right. And this means we have all studied that suppose I start with a function, this may be t by 2, this may be t by 2 and height is 1 by t. So, 1 by t and this like this t, area is 1. Okay. I call it delta, capital delta as a parameter capital T function of t. This does not qualify for delta t, because it is not 0 outside the origin. This says it should be 0 outside the origin, it is not 0 for here, it has got this much value. But second equation is satisfied, that area under it is 1. So, what do we do? We try to compress it. Height goes up, that is capital T we make smaller and smaller. So, its width goes down, height is 1 by t, that goes up, area remains 1. Still this is not 0 outside origin, like here, at all these points it is so much. So, you make it further narrower and it goes up further. So, finally, as t goes to 0, you have an impulse like function, and that is what this delta t is. Okay. It has another property, if I have another function say f t, then f t delta t, if you integrate, what will you get? So, that means, suppose I have got an f t and you have got this function. If you multiply, you will get something like this, okay, and then integral, you will get something. But this is not delta t. In order to make delta t, slowly I will make this t go to 0, it will become narrower and narrower. If it becomes very narrow, then this will be, say for instance, this is suppose very narrow. Then this function f t does not change much within this very narrow period, because even though my diagram shows it is so much, actually it will be approaching 0. So, f of t will be I mean f of 0 all throughout. That is, this is so narrow that whether this much or this much or this much, all values are approximately f 0. There is a value at the origin. Okay. So, if that be, what is the area? That is, I am repeating again, that suppose I have made this pulse very narrow and I am multiplying this by f t, this f t I am multiplying this by this. So, it will be very narrow, right. If this width is very small, the function f t over this entire period minus t by 2 to t by 2, its value will be approximately f of 0. It will not vary much because the width is so small. So, if you approximate the height to be f 0, area under this will be f 0 into what? Its height is f 0 into 1 by t, because pulse height was 1 by t, width was minus t by 2 plus t by 2. That was the pulse. I am multiplying by f t. So, new height will be approximately f of 0 into 1 by t. That is, I am assuming that for all the points from minus t by 2 t by 2, function value does not change. It is a very slowly varying function, its value does not change. Whatever value at the origin, it remains more or less that. Okay, this. So, height will be roughly approximately f 0 into 1 by t, width is 1 by t. So, area is product of the two f 0. And even if capital T goes down further and 1 by t height goes up, area will still remain f 0. So, in the limit this will become f 0. So, f t delta t dt integrated is f 0. You can then say f t delta t minus some point, say tau dt. This is nothing but the same thing, but the impulse is shifted, instead of here impulse is shifted to some point tau. Okay. So, the same phenomenon will come here. Okay. I have got two ends, tau plus t by 2 and this end is tau minus t by 2, that is tau is replacing origin, height is 1 by t, and the same thing here, this will be multiplied by the function. So, function over here, if this is the function, if the function f t goes like this, over this window it is like this much, but you can approximate this, you can assume that since this width is very small, the function is almost constant and it is the value it has at f tau. So, height now will be f tau into 1 by t after multiplication, width is again t. So, area under that will be f tau into t into 1 by t is the height and t is the width. So, it will be f tau. So, area under this will be f tau, and even if as t goes to 0, becomes very small and small, height goes up, but area remains this f tau. That means, f t delta t minus tau, it will be f of tau. Now, with these two properties, I bring something very interesting, which is called Dirac comb. Suppose I have got a periodic train of impulses. This is delta t, then at a gap of capital T you have got delta t minus t, then at 2 t you have got another impulse, dot 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 on this side also delta t plus capital T and minus t minus 2 t dot 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 dot. So, it is a periodic function, right, and period is t. Mathematically, you can write as though it is a superimposition of impulses delta t minus say n into t, n can be 0, 1, 2, minus 1, minus 2, so n is minus infinity to infinity. Let me call it S t. Okay. Now, you see S t, what is its? So, this is a periodic function, right. So, any periodic function and its period is from say minus t by 2 to t by 2, this much, period is capital T. Any periodic function can be represented in terms of Fourier series of this form. S t, this is from ordinary Fourier series knowledge. So, this you should be able to know, otherwise just go back to Fourier series and read it a little. S t will be summation of this complex sinusoids, where the basic frequency called fundamental frequency, sorry, this is capital omega naught. Capital omega naught is 2 pi by t, okay, and n times, so nth harmonic, n times this into time. So, it is a complex sinusoid, a function of time. It is a function of time. It is a complex sinusoid. It has got cosine component, sine component. If n is 1, it has a frequency omega 0 radian per second. We call it fundamental frequency. Otherwise, if n is 2, second harmonic, n is 3, third harmonic, like that. N is -1, -2, that is also possible. When you write it in terms of cos and sine, then n will take only 0, 1, 2. Okay. But this is a more general form. For any periodic function, not only this, for any periodic function of period capital T, you can write in a Fourier series form like this, where C n is the nth Fourier coefficient, nth Fourier series coefficient. That is the amplitude part associated with the nth harmonic. Okay, nth harmonic has this form, n into capital omega naught is the frequency. Okay. So, to the power j n into capital omega naught into t, corresponding coefficient is C n, is a superimposition of such coefficients. But these are discrete coefficients, because either C 0 or C 1 or C 2, there is either e to the power j omega 0 t, or e to the power j twice that, twice omega 0 t, or e to the power j thrice omega 0 t, so on and so forth, or minus 1 into omega 0 t, so on and so forth. So, some discrete frequencies, omega naught, twice omega naught, minus twice omega naught, minus 3 omega naught, plus 3 omega naught, like they are present. And in that case, C n, nth coefficient is given by this integral. This is there in the basics of Fourier series, everybody knows, and in case you have forgotten, you can just see the thing. You multiply S t by the nth harmonic with a minus sign and integrate over a period, you get C n, this is a formula. Now, this is a periodic function. For this periodic function, S t will be this. Now, from minus t by 2 to t by 2, if I integrate, I have only one impulse, others are not coming. So, which means it will turn out to be just this function e to the power minus j n omega naught t into 1 delta t only, other fellows are not present, because the range is from minus t by 2 to t by 2. And we have already seen a function f t times delta t integral. You can now integrate from minus n to infinity, you will get the same result, because delta t is outside, except for origin, you have the same, it has a value 0. So, if you now integrate, it will be value of the function at t equal to 0, but value of the function at t equal to 0 is e to the power 0, which is 1. Okay. So, this integral will give me nothing but 1. So, C n is 1 by t, which means, and this is independent of n. So, for every harmonic and fundamental, C n is common, it is 1 by t, which means S t is 1 by t this n into omega naught nth harmonic t. So, this is one important result, that this kind of S t periodic function is given by this. Okay. Now, I will come to this. This function actually is called a Dirac comb. It is like a comb, and if you take its Fourier transform, not Fourier series, it will be another comb. I am coming to that. Okay. But before that, this result. Now, why I am so bothered about doing all this is the following, that suppose I have this one analog function, I have one analog function, say x a t, and I multiplied this by this S t. Okay. So, that basically means I had one x a t, and I have got this impulses dot dot dot. If I multiply, I will get one impulse, but its height will be x a 0, then another impulse x a 1, like that. That is, if you integrate this, you will get x a 0. Area under that will not be 1, will be x a 0, then x a 1, which is strength. That is, if you integrate this delta x a, you will not get 1, you will get x a 0, x a minus t, x a t, like that. If you multiply these two, this into this, you will get this. So, this is a function suppose I got. Okay. I am just multiplying for fun. Then on this product function, suppose I want to take its analog Fourier transform. Okay, what will we get? That is the question. So, that means we have to carry out this integral x a t s t dt minus, sorry, e to the power minus j. We have to find out this at a capital frequency capital omega. Okay. We have to find out the Fourier transform of this at a analog frequency capital omega. So, you carry out this integral. Now, x s t, instead of this form, I can write it by this form also. So, this I bring inside this form. So, 1 by t, there is a summation inside. Okay. X a s t I am writing. So, x a t as it is, s t will be this, 1 by t has gone out, e to the power j n, some capital omega naught t, where omega naught, as I told you, is the fundamental frequency for this, that is 2 pi by t. T is the period, sampling period. T is where this is this Dirac, this impulse train is periodic over a period t. Okay, that capital T I am taking, all right, and from that I derive the fundamental frequency capital omega naught. That capital omega naught came here, n times that was the nth harmonic, a summation over all the harmonics, 1 by t outside. This is one part, and then e to the power minus j omega t dt. Now, I told you, whenever you come across double summation, next step is to interchange the two. So, this discrete summation can go out, and here you have got x a t for every n is getting fixed, and then you are entering this integral. For that n, you write x a t e to the power j, you combine the both capital omega minus n omega naught t dt. But what is this? This is nothing but analog Fourier transform of this guy at this much analog frequency. If you call it omega, capital omega prime, so it is x a t e to the power minus j capital omega prime t. So, it is analog Fourier transform of this at frequency omega prime, which means this is capital X A for analog Fourier transform. So, I remember capital X A j capital omega minus n omega naught. Okay. All right. So, if you want to, so this is one way, but that is if I take this product function, carry out its analog Fourier transform, we get like this. But on the other hand, On the other hand, if I use the other form, what is that? If I use this form here instead of the other form, what do I get? This form. All right, e to the power minus j omega t dt. Again, I interchange the two summations. This goes outside, this is inside. What you have is x a t e to the power minus j omega t, this part, this into delta t minus something. Now, remember I just a while ago I considered this, the some function f t into delta t minus tau. If you integrate, it becomes f of tau. All right. So, that means this is nothing but this function at n t. All right. Now, what is this x a n t? That is this function at n into t, this point. This is what I say nth sample x n, isn't it? X a, I mean, how I constructed them. If this is an analog function x a t, okay, x a t, you take one sample, then at t another sample. Okay. Nth sample that occurs actually at time point n into capital T, that is x a small t, if it is n into t, then this value I may call it x n, nth sample. When I draw a sequence of them, this is the same fellow x 1, 1, sorry x 0, 1, 2 dot 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 n. So, this x n is here and x n t is here, but they are same. Here at this x was time. So, at n into capital T point time, whatever is the value, that is this, and that I rewrite here, but as a function of index n only, nth sample, but they are same. So, that means this is nothing but x n and capital omega t radian per second into second is a digital frequency, only radian, you call it omega. So, you are left with to the power minus j omega n, which is dt f t. All right. So, that means we get a fantastic thing that if we multiply such an x a t by a train of impulses, okay, it is a periodic train of impulses with period capital T, then take Fourier transform of it, analog Fourier transform at analog frequency capital omega. What you get is nothing but dt f t of the sample train sequence at a digital frequency small omega, where capital omega and small omega are related by this. That comes from this approach. We have carried out the integral twice, but once we replaced S t by this formula, and here I replace S t by what is given, S t by what is given, that is impulses. So, by this approach, what I found out is that if you take x a t multiply by this impulse train, okay, and then resulting function, the product function, if you take Fourier transform, analog Fourier transform at frequency capital omega, analog frequency, what you get is nothing but discrete time Fourier transform of these samples. If you put these samples one after another, you get a sequence, discrete time Fourier transform of that at small omega, where small omega is related to your capital omega by this, that is the dt f t. but this is from the other approach equal to this one, which means I can equate the two. I can equate the two and say x e to the power j small omega from one approach, it is same as, that is the, what is this? This is DTFT. DTFT of what? If you take these samples, form a sequence like this 0th, first, no time here, all index values only. And so that this sample sits here, this sample sits here, this sample sits here, like the form a sequence. Call it nth sample x n, x 0, x 1 is x 0, x 1, x 2, x n. They are nothing but those values only, but not as a function of time, just as a function of index n. Then you get a sequence. Okay. And that is what I obtained here. I replaced nth sample value of the original analog function by just nth sample of the sequence. Okay. So, if you take the samples and they take their discrete time Fourier transform, okay, at a frequency small omega, that is same as this n minus infinity to infinity, there should have been an n here, capital X, that is analog Fourier transform, j capital omega minus omega naught, which is 2 pi by t. So, you can write 2 pi n by t, where this capital omega and this small omega, they are related like that. So, if you are finding out DTFT at a small omega, then you take the analog Fourier transform, where capital omega is small omega by t, okay, and you superimpose. So, this is the relation between analog Fourier transform and discrete time Fourier transform. This is what we will expand on in the next class. Thank you.